In this video, we'll go over the answer key for Friday, April 17th, where we are talking about enzymes. Now, enzymes are like catalysts, but they are different in that they are much faster than catalysts humans create. They work in way milder conditions than you would see like in organic chemistry where you need acids or high temperature. This works at body temperature at neutral pH for the most part. They are extremely specific. They will rarely, if ever, have any side products. And they can be regulated a lot. So, allosteric control, that means another molecule can bind it and either speed it up, slow it down, add a phosphate to it. You could turn something on, turn something off, or you could destroy the enzyme or create more of it inside the cell. Now, for enzymes, we usually classify them based on what reaction they do. So we have six broad classifications: so oxidoreductase, transferase, hydrolase, lyase, isomerase, and ligases. And for each enzyme, there's of course classes and classes of these until you get to a classification number that you can use to look up enzymes. And the number, you get four numbers, so they're class, subclass. So EC stands for enzyme commission, then class, subclass, and serial number. So this is class 4, subclass 2, subclass 1, and then serial number 3. So why do we need enzymes inside the cell? Well, the reason is normal reactions without any catalyst would be so slow nothing could be alive, as we know it at least. So we need enzymes to speed up those reactions for us to make life possible. Now let's look at how enzymes interact with our substrate, and there's two different models people go on. First is the induced fit model. So for the induced fit, when your substrate binds, it will bind loosely because it's not a great fit. However, upon binding your substrate, your enzyme will change conformation and bind your substrate tighter. That's the induced fit model. The lock and key is you have a perfect fit from the start. The substrate and enzyme bind perfectly to begin with. So, nobody knows exactly what model is correct. Some enzymes show one model over another. Excuse me. But the induced fit model is usually the one that's more generally accepted. People think that's how enzymes generally work. Not so much the lock and key model. Now, I did say that enzymes are specific. However, there are some enzymes that are more permissive. That is, they will allow substrates that they normally don't work on. So enzymes will catalyze reactions of related compounds. So for example, we have peptide and an ester. They look similar, and so the same reaction will be carried out by chymotrypsin. Alcohol dehydrogenase, what takes the ethanol that you drink and makes it acetaldehyde. Well, it will also take methanol and change it to formaldehyde and isopropanol, to formaldehyde, which is a poison. Isopropanol to acetone will also happen. Usually, these side reactions are slower than the main compound, but they do happen. So question 2 is really just a review of the previous slide: lock and key, perfect fit, induce, fit, binds, and then the enzyme changes. Now, enzymes usually, not always, but usually need something else to allow their reaction to happen. And these are called cofactors. So these cofactors, first we can split them into, is it a metal ion or is it a coenzyme? And a coenzyme we can split even farther to co-substrates and prosthetic groups. So what's the difference between these? Well, a prosthetic group is something that's permanently attached with the protein through covalent bonds. And we can think of heme. The heme's never going to be detached from your hemoglobin. It's there covalently. While a co-substrate can bind and then it can leave. That's another way we can control this enzyme's ability to do its chemistry. If we don't allow it to get the co-substrate, then we are preventing the reaction from happening. Now, if you go further in biochemistry or read about enzymes, you're going to come across terms such as holoenzyme and apoenzyme. The holoenzyme is everything there needed for the enzyme to do its reaction, while the apoenzyme is just a protein and no cofactor. Here is an energy diagram of a catalyst or enzyme in action. So we have the reaction of a bond switching. So if we look here, we have A and B bonded. We add C, and now B and C are bonded. So we start here and we go here. So reactants, products. At the very top, we have our halfway point of this reaction where we are kind of broken the bond between B and A, kind of, not all the way, kind of formed the bond between B and C, not all the way. This is called a transition state, and it's very high energy. And we measure the difference between the reactants in the top of this peak. That's called delta G double dagger. That is the free energy of activation. And the smaller this gap is, the faster your reaction goes. And we can calculate that by rate equals the exponent of negative delta G double dagger divided by RT. Now the other thing we need to know about these free energy transition state diagrams is the difference between reactants and products. That's called delta G. So if your products are lower, delta G is negative, that's spontaneous. If your products are higher, delta G is positive, that's not spontaneous, and you'll need to put energy into your system for the reaction to run. Now we can have more complicated transition state diagrams, and what I'm showing here is a reaction that takes 2 steps. Now we have 2 activation barriers. Whatever activation barrier has the higher energy of delta G double dagger will be your slowest step. And for our red line, the slowest step is the second step. Because if we were comparing A to this hump, that's delta G double dagger for our first reaction, then I to I double dagger. You can see this gap is much bigger. So delta G double dagger is much bigger in the second step. So that's how we can determine the rate determining step if we have 2 reactions. Also, you can see there's a valley of low energy between our transition states. This is called an intermediate, and you can usually measure this concentration during an experiment. But after your first reaction, your reactant will stay as an intermediate for seconds, minutes, milliseconds. It really depends on the reaction until it gets enough energy to go over the second reaction and become a product. Last thing I want to talk about is how a catalyst changes this transition state diagram. And all a catalyst does is it lowers the activation energy. The amount it lowers this energy is called delta G double dagger. Delta is weird. The reason why it's delta is because the difference between the reactants in the top of the hill is already delta G. So you're looking at the difference in the difference of delta G. So each triangle, each delta means difference. And so what happens with a catalyst is that you lower this activation barrier, and that makes this reaction go faster. We can calculate how many times faster using this equation, E delta G double dagger divided by RT. But importantly also, the thermodynamics, that is the favorability of a reaction, the equilibrium of a reaction, does not change with a catalyst. The energy of your reactants and the energy of your products are always the same regardless if you use a catalyst or not. Thermodynamics and kinetics are separate. You only speed something up. You cannot make a reaction more favorable using a catalyst. Alright, so based on what we talked about, what is the best description of an enzyme? That's B. It increases the rate the reaction approaches equilibrium. It doesn't make it extremely fast. Extremely, you can't really measure what extremely means, and it does not make something favorable. What component besides amino acids are sometimes necessary? That's the cofactor we talked about. 5. Look at this reaction and label the graph. So each time we get a hill, that's a transition state. The trough is our intermediate. Our products are higher energy than our reactants, so delta G is positive. It is not thermodynamically favorable. Our last question, our second to last question, is measuring rate enhancement. So we're looking at staph, and staph decreases the activation free energy of our reaction at 25. How much is it? Well, if we look at staph, we see that the rate enhancement is 5.6 times 10 to the minus 14. So we plug that into our equation. Rate enhancement equals E delta G double dagger RT. So our rate enhancement is 5.6 times 10 to the 14 equals this equation. Well, to get rid of an exponent, I have to take the natural log of each side. So natural log of our rate enhancement equals delta G double dagger divided by RT. R is given, T is in Kelvin. Then I just take these values, multiply it by, so I multiply both sides of the equation by RT, and I should get, if I did my math right, delta G equals negative 84,135.8, which means I lowered the activation barrier by 84 kilojoules, which is a lot. But you can see our rate is getting sped up by 100 million, which is a huge number. So it's 100 million times a million should give you times 10 to the 14th. So yeah, our speed is going incredibly fast with our enzyme. Our last problem is now using well, it's actually using the same equation, just a little bit differently. So we have a enzyme that makes one hydrogen bond. The energy of this hydrogen bond is minus 40. What is the rate enhancement? So if this hydrogen bond is minus 40, that means delta G double dagger would be 40. We have lowered the energy by 40. So I want to calculate the speed. So E 40,000 divided by RT equals the speed up of 1 million. And that is it for this video. I will see you in the next video.